In this video, we're going to talk about matrices slightly more generally. So we're going to do some arithmetic operations on matrices. So matrices are useful beyond just solving linear equations, although that is where we're headed, is to see another way to solve linear equations. But in general, matrices can be used just as a vice for storing data. So remember I said that it's a box of numbers, so you could think of it like a spreadsheet where the rows and the columns have meanings and the numbers that are inside represent some important data that you need to store. So we're gonna, when we talk about matrices in more generality, we use regular matrices, so we're not going to be using augmented matrices here. So there will be no vertical line, okay? Because they're not representing systems of equations. So when we want to describe a matrix to somebody, we usually want to talk about how many rows and how many columns it is so that people can get an image as to what the matrix looks like. Okay, this is what we call the size of a matrix. So it's the number of rows by the number of columns. Okay, so the size, you're going to write number of rows and then an X number of columns. So it's like a dimension. Okay, so you would say this room is 9 feet by 12 feet. Okay, we're going to say the same thing about matrices. So it has this many rows and this many columns. So for the first matrix here, we can see that it has 2 rows and 3 columns. So we would say its size is 2 by 3. Okay, and the next one, we have 4 rows. Okay, so these 4 rows, 2 columns. So we would say it has size 4 by 2. So when you read the X, okay, you read it as by. The last one has 3 rows and 3 columns. So it's a 3 by 3. Now we often want to talk about an entry in a matrix. Okay, so we would write it as a little a, and then we have 2 sort of subscripts, let's say M and N. So this would be the entry in, say, matrix A that's in row M and column N. Okay, so if we wanted to describe, say, I don't know, this 4 here, this entry, we would write 4 is the second row, third column. So we would write A, 2, 3 for that entry. Okay, so it's always rows and then columns in every scenario. So there's some special names for some special matrices. So if your matrix has only 1 row, okay, it's called a row matrix. You might also see it referred to as a vector, okay, if you're looking at a linear algebra textbook. So for an example, if we had, I don't know, okay, 2, 1, -1, 0, okay, so that would be a 1 by 4 matrix. Okay, so that would be its size, and it would be a row matrix. A column matrix similarly has 1 column. Actually, maybe I'll just write here. So these definitely will have size 1 by n. Okay, so that n is the number of entries, because there's only 1 column, or 1 row. So the column is similar, except that you only have 1 column. Okay, so for example, we could have 5, -7, and 8 in 1 column. So this would be a 3 by 1 matrix, because there's 3 rows and only 1 column. So these column matrices always have size, size m by 1. Okay, and they have m entries in them because there's only 1 column. Another special type of matrix is called a square matrix. Okay, so if it's square, it has the same number of rows and columns. Okay, so square means that the size is n by n. So the number of rows and the number of columns is equal. Okay, so for example, maybe you have this matrix here, which is a 2 by 2 matrix. This is actually a special matrix that we'll talk about later. This matrix up here in the last example, okay, it was 3 by 3. So we would call that a square matrix. Okay, so that's another example of a square matrix. So we're going to talk about some operations that we use on matrices. So there's going to be 4 in total. We're going to do 3 in this video. So the first one is equality, which seems like a funny operation, but for matrices it's not totally pointless. So we say that 2 matrices are equal if they have the same size. So they have to have the same number of rows and columns, and all corresponding entries are equal. So they have to look identical. Okay, so here's an example. So if we have these 2 matrices and we want to say they're equal, we want to find x to make them equal. Well, first of all, we would notice that they're both 2 by 2 matrices. Okay, so they have the same size. So that's a good start. Otherwise, they couldn't be equal. And now we want to compare the corresponding entries. Okay, so we need the first entries in row 1, column 1 need to be equal. Okay, they are. We also need entries in row 1, column 2 to be equal. And row 2, column 1, those ones should be equal. And lastly, row 2, column 2 should also be equal. So this gives us 4 equations. Okay, so we need, okay, so 1 equals 1. 2 should be equal to x. 3 should be equal to 5 minus x, and 4 should be equal to 4. Okay, so these first one and the last one, they're obviously true because they're just numbers and they're the same number. So what we want to do is solve for x, the system, x equals 2 and 3 equals 5 minus x. Okay, we can do this with substitution or any other method that you'd like. I made it pretty obvious, hopefully. So if x is equal to 2, then 5 minus x is going to be 5 minus 2, which is 3, okay, which is as desired. Okay, so our only solution that would make these 2 matrices equal is when x is equal to 2, because then the x equals 2 equation is satisfied, and also the 3 equals 5 minus x would also be satisfied. Okay, now one note I want to make about equality, okay, they need to be the same size. So if you had a matrix like this, 1, 2 in the first row, 3, 4 in the second row, and you wanted to compare it to the matrix that looks like this, so the first row is 1, 2, 0, and the second row is 3, 4, 0. So they look similar. Okay, the first 4 sort of entries match, but there's these extra zeros. It's tempting, because there's 0, to just discard them and say that this is a 2 by 2 matrix. But we want to remember that they're placeholders for data. So it's possible that knowing that these are 0 is very important. Okay, so the size here, this one is a 2 by 2, and this one is a 2 by 3. Okay, so these are not equal. Okay, they don't have the same size. Even though they look similar, they are not equal. Okay, and another time, but people sometimes get confused. Okay, maybe they are the same size, but the entries are just a little mixed up. Okay, so here all I've done, so they are similar, they use the same numbers, but the first row, it doesn't look the same. Okay, so remember, the columns have meaning. So the 2 in column 1 is different than the 2 in column 2. Okay, so again, these are not equal. They have to look identical. So they have to be the same size with all the numbers in the same place. So what about addition and subtraction? So there's times where we can not do this. Okay, so we can only, okay, add or subtract if the matrices are the same size. Okay, so we need them to have the same number of rows and columns. Okay, if they are the same size, then we are able to add or subtract. Okay, so the way that we do that is probably how you would guess. Okay, we simply add or subtract, depending on the operation that you want to do, corresponding entries. Okay, so let's do a couple of examples. So in this first one, I have a 2 by 3 matrix adding to a 2 by 3 matrix. Okay, so they're the same size. Okay, so that's good. We're able to add. And then what we're going to do when we add them is we're just going to add corresponding entries. Okay, so let me just get the highlighter out. So the 1 I'm going to add to the 3, and that's going to stay in the first entry. Okay, and then I'm going to do the -3 and the 2, and that's going to go in the second column of the first row. Okay, I do the 0 and the -5. That's going to go in the third column of the first row. So this is going to be -3 plus 2, 0 plus -5. Okay, now I want to do the same thing with the second row. Okay, so the 2 plus the -6 is the first entry. Okay, and then I have the 6 and the -1 as my second entry. And then lastly, I have 1 and 0. That's going to be my second row, third column entry. Okay, so if I simplify this, I'm going to have 4 minus 1 minus 5 for my first row. Second row is -4, 5, and 1. And notice that the size is the same. I still get a 2 by 3 matrix. Okay, let's try another one. Here, they're both 2 by 2 matrices. Okay, so we're able to subtract. That's good. And then we're just going to do the exact same thing. Okay, so you just do the entries in the same positions. So I'm going to have 0 minus 1. So I want to make sure that I'm doing a minus here. Okay, so the minus is what goes in between. The next entry, I have 2 minus 0. Then I have 7 minus -2 and 8 minus 5. And I'm just going to color code those for you. Okay, now I just want to simplify. So 0 minus 1 is -1. 2 minus 0 is 2. 7 minus -2 is actually add 2, so that's 9. And 8 minus 5 is not 5, it's 3. Okay, again, I still got a 2 by 2 matrix. Okay, part C, my first matrix is a 2 by 1. Okay, and again, I tried to trick you. It's tempting to just get rid of this column because it's all zeros and say I also have a 2 by 1, but I actually can't. Okay, this is a 2 by 2 matrix, so the operation addition is not defined. So this is since the matrices are different sizes. Okay, so we can't even do that operation. Okay, The last operation we're going to talk about in this video is called scalar multiplication. Okay, scalar is probably a word that you maybe haven't heard before. When we say scalar, we just mean it's a real number. Okay, so what I'm doing is I'm taking a matrix and multiplying it by a number. Okay, so when we perform scalar multiplication, we simply multiply every entry of the matrix by the scalar, or the number. Okay, so maybe I'll put a note here. This operation is always defined. Okay, so if we want to multiply by a number, we can always do that. So here I have an example. So I want to do 4 times this matrix that is a 3 by 2 matrix. Okay, so what I'm going to do is I'm also going to get a 3 by 2 matrix, and I'm just going to times every entry by the 4. Okay, so you put the 4 into every single entry. I still have a 3 by 2 matrix, so this doesn't affect the size. So my resulting matrix is going to be 4, 0, -4, 20, 16, and 8. So when you want to multiply a number times a matrix, you can always do it, and you just multiply every entry in the matrix by that number. Okay, we'll do one more example that sort of combines all of these ideas. So suppose I want to solve for x and y, and I have what we call here a matrix equation. Okay, so I have 2 times this matrix minus 3 times this other matrix equals some other matrix. Okay, now notice all the matrices that are involved are 2 by 2s. Okay, so the scalar multiplication is always defined. Okay, but I'm going to get a 2 by 2 when I put the 2 in, and a 2 by 2 when I put the 3 in. And then the subtraction will still be defined because I'm going to have a 2 by 2 and a 2 by 2. Okay, so in order to solve this, what we want to do is take the side that looks worse. Okay, let's simplify this side so that it looks nicer. Okay, so what I'm going to do is I'm going to first put in the 2 and then the 3. So this is going to become 2x, 8, 6, and 2y. And then I'm going to put the 3 in. Okay, so I have 3y, 3, 0, and 12x. And that should be equal to the other side, which we haven't done anything to. Okay. So I did the scalar multiplication for both. Now, one thing I want to point out, I put the 3 only in. Okay. You could, if you wanted, put in a -3, but then this symbol here is going to be plus. Okay, so don't get confused that you put this in, it's going to be times. Okay, this is a minus sign, not times -3. If I meant times -3, well, I wouldn't write it like this, but there would be definitely brackets around the -3. Okay, so it doesn't look like a minus. Here it's minus, so we're subtracting these matrices. Okay, and we can subtract these because they're both 2 by 2s. So I'm going to have 2x minus 3y in the first entry. And then I'm going to have 8 minus 3 in the second entry. 6 minus 0 in the second row, first column entry. And then 2y minus 12x in the row 2, column 2 entry. Okay, so that should be equal to this other matrix. Now I'm just going to simplify slightly. So the x's and y's are not like terms. They can't go together, but 8 minus 3 is 5, and 6 minus 0 is 6. Okay, so I want to find x and y so that these two matrices are equal. So that means that I need the corresponding entries to be equal. Okay, now some of them are immediately equal. Okay, so the 5 and the 5 are the same. 6 and the 6 are the same. So the yellow and the green things are fine. So what we need to do is solve the system of equations 2x minus 3y equals negative 11, and 2y minus 12x is equal to negative 14. So we want to find x and y that satisfy those equations. So you can use any method you want, because obviously it doesn't tell you here which one to use. I'm going to use Gauss-Jordan elimination just for practice, but I want to be careful because notice that I have x's first and then x's second. Okay, so you want to make sure that you think to change these around so that they match up. Okay, so when I put this into a matrix, I'm going to have 2, negative 3, and negative 11. And then I'm going to have negative 12, 2, and negative 14. Okay, and then we want to pivot around this entry. Okay, so the first thing I'm going to do is divide by 2 for row 1. So that's going to give me 1, negative 3 over 2, and negative 11 over 2. Okay, I'm still pivoting around this entry. Okay, so I now want to make the negative 12 a 0. So my next step should be row 2 plus 12 of row 1. Okay, so I'm not changing row 1. But now I want to change row 2. Okay, so I have negative 12 plus 12 times 1. Okay, that's going to give me a 0. That's what I wanted. And then down here, I have 2 plus 12 times negative 3 over 2. So that's going to be 2 minus, so the 2 is going to cancel here and make this a 6. So it's going to be minus 18. So what I'm going to get is minus 16 there. Okay. And then I want to do the last one. So it was a minus 14, and then I want to add 12 times negative 11 over 2. So this is going to be negative 14. The 2 again is going to cancel with the 12, so I get a 6. So it's minus 66. So that's going to be negative 80, I believe. Okay, so now I'm done the pivoting in column 1. So I want to now pivot around this entry, the negative 16. So my first step is to take row 2 and divide it by negative 16. So row 1 isn't going to change. Okay, and then row 2, I'm going to have 0, 1, and then negative 80 divided by negative 16 is 5. Okay, so then my last step here, I'm still pivoting around that, but I want to make the negative 3 over 2 into a 0. So I'm going to do row 1 plus 3 over 2 row 2. Okay, so those are going to stay the same. Okay, this is going to become a 0. And then this entry up here, I had negative 11 over 2, and I want to add 3 over 2 times 5. So that is negative 11 over 2 plus 15 over 2, which is going to be 4 over 2, which is 2. So I get the integer 2. So my solution, which I don't have a lot of room for, okay, is x equals 2, y equals 5. Okay, so if you plug those in to your initial matrix equation, okay, the two sides will be equal. They'll be the exact same matrix. So I encourage you to check that. Remember that you did not have to use Gauss-Jordan elimination here, okay? It didn't tell you to do that. It's just new to us.